Hello, this is Jude Socrates, and welcome to A Portrait of Linear Algebra. So our video for today is the second of 3 videos, and these are about eigentheory. So our first video introduced the concept of eigentheory. So we said that if you have a square matrix, then an eigenvector for that matrix is a non-zero vector, so that when you multiply A by that vector, you get a vector which is parallel to your original vector. So in equation form, we said we want A times B to be some lambda times V, where the lambda is a real number. So in this video, we're going to explore the geometric nature of eigentheory. So we already know it has to do with parallel vectors, okay? Transforming V to a vector which is parallel to itself. And we're also going to see some techniques, some computational techniques that will help you find the eigenvalues of 3 by 3 matrix, 4 by 4 bigger matrices, and to find the eigenvectors. So for our first topic, we are going to review the projection and reflection operators that we saw in R2 and in R3. So this was the example that we saw in that video back in chapter 3, I believe it is section 3.2. And these are the matrices that we obtained in that video. So let me scroll down a little bit further so that we can see, there you go. We can see all 3 matrices, okay? So what are we going to do? Well, first, let's just play, all right? So I have a sample input vector, -3, 1, 6, and let's see what happens when we find its projection on L, on pi, and its reflection across pi. Okay, so we write down V vertically as a column matrix, and then let's find out, okay, what's your answer? All right, and let's approximate that. Okay, now how about the other 2? So let's copy, and here, and what do we get here? Okay, and we get that, and lastly, this, and that. Okay, so yeah, they're kind of ugly, but what do you expect? I mean, there's 65 in the denominator. Any chance that any of these vectors are parallel to the original vector? Okay, well, the good thing is that we have a 1 over here, and that's a negative 1.6. So the only way that these 2 will be parallel is if we multiply the original vector by negative 1.66. Do we get the other 2 components, though? Will they be correct? No, that will be a positive 5 something. Okay? So similarly here, you will have to multiply by 2.66. 6 times 2.66, way bigger than 4.6. Here, 4.3, 6 times 4.3, way bigger. Okay? So none of these 3 vectors is parallel to the original vector. But let's take a look anyway. Ooh, so pretty. Just kidding. So here we are. It's been a while since we played around in Algebra. But let me show you what I've created on this diagram. So we have our plane and we have our input vector, except it's called U. That's fine. We have the normal line. That's in light blue over here. And then we have the 3 output vectors. So here's the first one, and it was the projection on L. Okay, it's this vector, and obviously it has to be on L. And similarly, V2 is the projection on the plane pi. So this has to be on pi, and let's rotate a little bit, and yeah, as you can see, that vector is on pi. And the third vector is the reflection of our vector across from pi. Okay, so that looks pretty convincing, right? That red vector is a mirror image of our original vector across plane. Okay, so what does this have to do with eigentheory? We already said these are not eigenvectors. These three vectors, none of them are eigenvectors. I'm sorry, this orange vector is not an eigenvector for any of the three operators because none of the outputs are parallel to that same input. Okay, so how are we going to create eigenvectors? Well, that's why we're looking at this diagram. Can we input a vector so that its projection on the line is parallel to the line? That doesn't work. Well, if you want it to be parallel to the line, then it looks like it has to be on that line itself. Okay? And similarly, if you want to project the vector onto pi, and then the answer is parallel to pi, looks like the only way to do it is if that vector is already on pi. Okay? But, however, let's keep thinking about that. If your vector is already on pi, what will be its projection on the line? Okay, what will be its shadow on the line? It won't have a shadow. Or rather, its shadow is just the zero vector. Ooh, so you want it to transform to the zero vector. Huh, where have we heard that before? It's the kernel. Okay, so what about the reflection? Okay, how can you input a vector into the reflection so that you get a multiple of that vector? Well, I guess if you're already on the plane, it's like you have a mirror and then you put a 10 on that mirror. Okay, its reflection is practically that same object. Okay, so if the mirror were actually embedded, if the pen were actually embedded in the mirror, then it will have itself for its reflection. But is there another way to do that? So what if you were on the normal line and you reflect across the plane? Then you would be in the exact opposite direction, but you will have the same length. So is that an eigenvector? Yes, and what's its eigenvalue? Opposite direction, same length, -1. Okay, so let's go back to our notes and see if our suspicions are right. Okay, so here we are. I guess we should do a little housekeeping here. We are going to input new vectors. Okay, so we said if you're already on the line, then its shadow on the line should be itself. Okay, so the simplest vector on that line would of course be 2 minus 6, 5 itself. All right, so let's see what happens. And I guess I can clean this up as well. Boom. Oh, okay, yes. So its shadow on the line is itself. Now, of course, it doesn't have to be that exact normal vector. It could be any multiple of that normal vector. So we could have 4, -12, +10. Okay, and of course, by homogeneity, yeah, we get exactly the same vector. Okay, so what about if we found the projection of that same vector on the plane? So you're on the normal line and you're taking the shadow on the plane. Okay, will it have a shadow? Oh, sounds like something similar that we did. If your vector is already on the plane, its shadow on the line will be 0. So this is backwards. If you're already on the line, then its shadow on the plane should be 0. Yep, so it's in the kernel. It's in the kernel of the projection operator. And what do we say? If you are on the line and you reflect across the plane, then you'll be facing the opposite direction, but it will be the same length. Okay, so that's an eigenvector, but with eigenvalue -1. So let's see, does it work? Oh, hang on a second. Reflection across pi. Maybe I should do that. There we go. So yeah, now we have a negative, the opposite sign in all three components. Okay, so as a recap, okay, so that output, you can think of it as 1 times the original vector. Okay, so that eigenvalue is 1. And for the second one, we can think of it as 0 times the original vector. Okay, it's the kernel. And for the last one, we can think of it as -1 times the original vector. Okay, so that input vector, which is on the normal line, is an eigenvector for all three operators. All right, so now let's see what happens if your input vector is on the plane. Okay, 2x minus 6y plus 5z has to be 0. Okay, how can we make a vector on that plane? Well, an easy way would be to make one coordinate 0 and then play with the other 2. So you want 2x to cancel with 5z. So if I make x 5, I'm going to get 10. So to make 5z cancel with 10, z has to be -2. Okay, 10 minus 10, 0. Okay, so let's see what happens if you project this vector, which is on the plane, onto the line. The 0 vector. Okay, so again, we said that this means that this vector is in the kernel of the projection onto the line. What if we project the same vector on the plane? It's already on the plane. So what happens? You get exactly the same vector, right? What if you reflect it across the plane? Okay, so that was the pen on the mirror analogy. If you multiply them together, what do you get? The same vector. Okay, so again, we can think of this as 0 times our input vector. And we can think of the next one as 1 times our input vector. And the last one is also 1 times the input vector. Okay, so we have eigenvalues of 0, 1, and 1. Okay, so let's think a little bit more about the kernel. Okay, so we said that an eigenvector cannot be the 0 vector, but there's nothing stopping us from having the real number 0, the scalar 0, as an eigenvalue, okay, our lambda. So what happens if we allow lambda to be 0? We want a times b to be lambda times v. 0 times v is a 0 vector, okay? So that means, again, that v has to be in the null space of the matrix A, also known as the kernel of the operator corresponding to A. Let's think some more about how this relates to the characteristic polynomial, p of lambda. We defined it to be the determinant of lambda times the identity minus A. What happens if you plug in 0? Okay, then you get 0 times identity, 0 matrix, minus A. So that just becomes minus A. Okay, but remember, if you multiply a matrix by a scalar, let's say k, remember that theorem? The determinant of k times A is k to the power n times the determinant of A, because each row gets multiplied by k, so therefore you have an extra factor of k n times, so that's k to the power n. Okay, but our k is -1 to get minus A. All right, so it's -1 to the n. So what does this mean? If p of 0 is 0, then the determinant of A has to be 0. Okay, because -1 to the n is not 0. So conversely, if the determinant of A is 0, then p of 0, by simple substitution, has to be 0. Okay, so we can now add this condition to the last one that we saw when we talked about determinants. Okay, the first key property of the determinant function as the litmus test for invertibility. We had 25 conditions in section 3.8, I believe. So now we get to add 2 more conditions, although one of them was in chapter 7. Okay, so if A is a square matrix, then the condition that A is invertible is equivalent to both of the following. The determinant of A is not 0. That's our litmus test. And from here, lambda equals 0 is not an eigenvalue for A. So what did we see in our 2 examples? 3 examples, rather. For proj L and proj pi, we both saw eigenvectors for lambda equals 0. Okay, so neither of those 2 matrices is invertible. Okay, but for the reflection, we only saw eigenvectors for eigenvalues 1, where your vector is already on the plane, and -1, where your vector is on the normal line. So the reflection across the pi is an invertible operator. All right, so the second half of this video is about computational techniques. And, well, basically what I want to show you are a couple of theorems that will help you figure out the characteristic polynomial and to find its roots, okay? In all honesty, of course, if you have a graphing calculator, then it's very easy to find the roots of polynomial or to factor it completely for you, okay? So here is something you can use if all the entries of A are integers. When you get the characteristic polynomial, every entry is an integer. So when you expand it out, as we're going to see in our example, every coefficient will be an integer. Okay? And again, the highest term in that polynomial is lambda to the n. Okay? So the integer roots theorem tells us that if you have this polynomial with integer coefficients and the highest term has coefficient 1 and the constant term C0 is not 0, then all the rational roots of this polynomial are in fact integers. And if x equals c is an integer root of the polynomial, then c has to be a factor of the constant coefficient c sub o. Okay? So if you're looking for integer roots, try the divisors, the factors of c sub 0. Now what happens if you have a matrix where the entries are rational numbers? Maybe some of them are integers. Okay? So what's going to happen? Well, again, you're going to expand, but this time you might have denominators in some terms. Okay? But we want to look for the roots, so set that equal to 0, and then we can clear the denominators. Okay, multiply both sides by the LCD. Okay, so this time the coefficient of lambda to the n might not be 1. Okay, so there might be a c sub n as coefficient for lambda to the n, but we can still make all the coefficients integers. Okay, So the rational roots of this polynomial now have to look like c over d, okay? An integer over another integer, okay? The numerator c has to be a factor of c sub o, so that should sound familiar. But now the denominator d has to be a factor of the leading coefficient c sub n, okay? So if you had a 3 over there, for example, you have 3x to the fourth power. You have a 4 by 4 matrix, or to be more precise, 3 lambda to the fourth, okay? Then your rational roots might have a denominator of 1, or a denominator of 2, or, I'm sorry, I said 3 lambda to the fourth. Okay, the coefficient is 3, not 4. So your denominator could be 1, or it could be 3. All right, so let's look for the characteristic polynomial of this matrix. And of course, later we will look for the eigenvalues, and we will find the basis for each eigenspace. Okay, so we said we want lambda times the identity. So fill this up. Might as well do the zeros first. And we have lambda along the diagonal. And we subtract 8. Lambda I n, lambda I 3, minus 8. Okay? So we have to subtract these entries from the first. So minus 21, minus 72, positive 24, positive 8, lambda plus 27, negative 8, positive 8, and then positive 24, and then negative 5, lambda minus 5. Okay, so we need the determinant of that matrix to get our P of lambda. There's the Greek lambda. Okay, so remember how to do a 3 by 3 determinant. One easy way is to just copy the first two columns to the right, and then we go multiply, 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 add together, multiply, 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 subtract. Okay? So yeah, if your matrix is not triangular, it's a little bit messier, or maybe the word is tedious, a little bit more tedious to find the characteristic polynomial by hand. Okay, you now have a lot more terms. That's 2 negatives, so that's going to be positive. So it will be plus 72 times 8 squared is 64. Simplify as we go. And then we have 24 times 8 times 24. So that will be plus 24 squared times 8. Okay, and then we will subtract 3 terms. Okay, so 8 times 24 times lambda plus 27, which I already have here. Steal that. And then, okay, so we're subtracting, correct? And then we'll subtract this. So that will also be a plus. Plus 8 times 24. So I'll just copy that. Times lambda minus 21. I will copy that. And lastly, we have minus, but there's a minus 72 there. So that's plus 8 times 72. 8 times 72 multiplied by lambda minus 5. Okay, so let's just double check. We have these three together, and then that's a positive contribution, 72 times 64. Positive also, 24 squared times 8. Okay, now go backwards. There's a minus 8 times 24, and 27. minus also, but there's a minus 8, so it's plus 8 times 24 lambda minus 21. And then plus 8 times 72 times lambda minus 1. All right, so although it is messy, it's really just arithmetic and algebra, okay? So yeah, we know how to compute that number and then distribute to lambda minus 5. The other two are the same idea, okay? We know how to plug that into a calculator, It's really just the first term that's really messy, okay? So you know what? Why don't we get a little help from Maple? Who is that? Okay, so that's 576 lambda minus 28, okay? And so on, okay? Let's just work backwards because these are the easiest ones to distribute. Who are you? Okay, so we have that. And then who else do we have? So I might as well just start adding them up. Okay, and then who do we have here? There's a minus here. Okay, so that's what we have. And add that to the rest. Okay, there we go. We just fix this a little bit. Okay, that's better. And the last three terms, we have these two numbers. We can compute them together. Okay, who do we have? 9216. Okay, so let's add that to the rest. Okay. All right. So we can simplify everything but the first term. Okay. So that's what we. Okay. So we have everything but the first term. So let's bite the bullet. We need to expand this out. Okay. So if you're doing this by hand, what you could do is, well, expand them, these two factors first. Okay, so we know how to FOIL. We'll get lambda squared plus 27 minus 21. So that's plus 6 lambda minus 21 times 27. Punch that into your calculator. And why did you not distribute for me? So I should do compute expand. There we go. So as I said, there will be a 6 lambda. 21 times 27 is 567. Okay? And then what you will have to do is you will distribute to lambda minus 5. Okay? So you'll get lambda cubed, 6 lambda squared, minus 567 times lambda, and then minus 5 lambda squared, minus 30 lambda, plus 5 times 567. Okay? So if we let Maple do that for us, do the messy stuff for us, compute, expand, there we go. That's what it will come down to. Okay, so our final P of lambda, we can now add it all together. Our P of lambda should be, the first term is this, and then we will add the 576 lambda minus 28. So we will get, there you go, lambda cubed plus lambda squared minus 21 lambda minus 45. So even though it started out with big numbers, they got simple real quick. All right, so at this point, we have P of lambda, and now we want to solve for the eigenvalues, and that means set that equal to 0 and find the roots. So as I mentioned, if you had a graphing calculator or a computer, you could ask it to factor you. That would be the simplest way. Or you can graph that polynomial and eyeball the roots and see if they actually work. I'm going to give you a review of synthetic division, and we are going to use that to find the roots of this characteristic polynomial. So what did the integer roots theorem say? Look at the constant coefficient, negative 45, and the rational roots of p of lambda are actually integers, and they have to be factors of 45. Okay? They could be positive or negative, actually. We don't know. However, I did not mention something to you, which is called Descartes' rule of signs. You look for the sign changes in the consecutive terms, and what do we see? Okay, from here to here, no sign change. From here to here, we have a sign change. From here to here, no sign change. So there's exactly one sign change in the consecutive terms of p of lambda. Descartes' rule says you will have exactly one positive root. Okay, so as a bonus, we can keep our fingers crossed and hope that the roots of p of lambda are really integers. And if so, then they should be divisors of 45. Who are the divisors of 45? Okay, so of course 1 is always a divisor of any integer. Not 2, but 3 is. Not 4, but 5 is. Not 6, not 7, not 8, oh, but 9 is. And so on. Okay, so let's hope that we find it very soon. Okay, so here's how synthetic division works. Okay, here are your candidates. You're going to put our first candidate on 1. Okay, I have these 4 rows. Okay, we're going to fill this up. Drop the 1 so it goes down here. That's always the first step. Drop this number down to the bottom. And of course, because p of lambda always starts with lambda at the end, that first number is always going to be 1. And then what do? You do 1 times 1, which is 1. You put that over here. My apologies, over here. Okay? And then what do? We add them together. So we're going to get 2. Okay? And then what do? 2 times 1 is 2. We're going to get that over here. Okay? And add them together, you'll get negative 19. Okay? Negative 19 times 1 is negative 19. Unfortunately, that's not going to be 0. So we're going to get 14, negative 64. Okay? So that negative 64 actually has a meaning. Okay? Where do we see it? Well, here's our polynomial. Okay? What if we replaced lambda with 1? 1 cubed is 1. 1 squared is 1. Minus 21 minus 45. And guess what? We get minus 64. Ooh. So that number that you get here is actually the value that you get when you plug in what you're dividing into p of lambda. Okay? So if you want a root, that remainder had better be 0. Okay? Alright, so that didn't work. Sadness. So let's start over with our next root, which will be. Okay, my apologies. I said our next root. I meant our next candidate, which is 3. Okay, 3 may or may not be a root. So now we have a 3 over there. And I did miscount. I only needed 3 rows, not 4. Okay. Same first step, just drop the 1. 1 times 3 is now 3. 1 plus 3 is 4. Okay? 4 times 3 is 12. Negative 21 plus 12 is negative 9. Okay? Negative 9 times 3 is negative 27. So again, that's not 0. Okay, that's going to be negative 72, I believe. So again, if you plug that into our p of lambda, minus 21 times 3 we should get negative 72. Is that it? Yep, negative 72. Alright, I didn't want to scroll down, so I thought, you know what, let's use our first table here. Next candidate is 5, so put 5 over here, drop the 1. 1 times 5 is 5. 5 plus 1 is 6. 5 times 6 is 30. Ooh, 30 minus 21 is 9. 9 times 5 is 45. Yay! So finally, we get 0. Okay, after 3 tries, we get 5 to be an actual root of the lambda. As a bonus, okay, these numbers here have a meaning. Okay, that is actually, those are the coefficients of lambda squared, lambda, and 1 after we factor out lambda minus 5. Okay, the root is 5. The factor is lambda minus 5. Okay, so let's write that up here. We want it factored. So one factor according to the chart is lambda minus 5. And the other factor is lambda squared plus 6 lambda plus 9. Okay? Now, if you don't believe me, let's expand. Lambda cubed minus 5 lambda squared plus 6 lambda squared. 6 minus 5 is 1. Okay? And then where were we? Minus 30 lambda plus 9 lambda is minus 21 lambda. Last term, minus 45. Okay? But of course, I hope you recognize that that second factor is, of course, perfect square. So that is lambda plus 3 quantity squared. Aha. Okay. So therefore, we get our eigenvalues. They have to be 5 and negative 3. There you go. Lambda equals 5 and negative 3. Put them in increasing order. Negative 3 goes first, followed by. Okay, now once we know the eigenvalues, the rest is going to be relatively easy. Right? So we want to find a basis for each eigenspace, one at a time. For lambda equals negative 3, we want to find a plus 3 times the identity. Okay? Minus minus 3 is plus 3. So we will take our A and we will add 3 along the diagonal. Being careful with the sign. 21 plus 3 is 24. Minus 27 plus 3 is minus 24. 5 plus 3 is 8. Ooh, look at what happened. Okay, so we're definitely going to get a row of zeros because these two rows are exactly the same. But that also looks suspiciously like a multiple of this. And yes, look. If you multiply by negative 3, you will get those numbers. Ooh. So we're going to get 2 rows of zeros. Compute matrices. REF. Bingo. We get 2 rows of zeros. Okay? Let's do the other REF, and then let's write down a basis for each eigenspace. Okay, so for lambda equals 5, we want to find a minus 5 times the identity. Okay, so we take a, whoops, wrong place, over here. And we subtract 5 along the diagonal. Okay, 21 minus 5 is 16. Minus 27 minus 5 is minus 32. And 5 minus 5, ooh, that's interesting. We're going to get 0. Interesting. Okay, it's not obvious that we will get a row of zeros. So let's see. Compute matrices RAF. Thank goodness. Okay. We still get a row of 6. Okay, we're at the home stretch. So now we will sight read the null space to make a basis for the eigenspace. Okay, leading variables. There's only one, x1. So x2 and x3 are free. All right. So our eigenspace is two-dimensional. We need another vector there. Our free variables are at the second and third. So anything below that 1 has to be a 0, and we have a free variable in x3. Okay, so the -3 here will go to the first coordinate in the first vector, and then the -1 will go to the first coordinate in the second vector as positive 1. Okay, check. So we have to make sure that when we multiply these vectors to the original matrix, we will get -3 times that vector. Okay, you know what? I see a 1, 0, 0 here. So let's test the second vector first. 1, 0, 1. Okay, we should get -3, 0, -3. And we do. Yay. Okay, so now we multiply by -3, 1, 0. Oh, look at that. I can now recycle this as -3, 1, 0. Okay, do we get +9, -3, 0? Let's see. Yep, +9, -3, 0. Okay, last task. We need the null space of this matrix. So leading variables x1, x2, free variable x3. So it is only one dimensional, and the free variable is x3. So 3 goes into the first component as -3, and -1 goes into the second component as +1. Okay, so this time our eigenvector is -3, 1, 1. So let's check. The eigenvalue though is 5, not -3. So we should get -15, 5, 5. Do we get it? We get it. Yep, we get it. Okay, wonderful. So that is our video for today. Thank you very much for watching. This is Jude Socrates signing off. You will find me on Facebook, and you will find the 4th edition on Facebook and at kendallhunt.com. So enjoy the rest of your day.